Hello everybody and welcome to Nuclear Physics Lesson 1. At this point, if you haven't already completed the Rutherford research task on the discovery of the nucleus, please make sure that you go away, complete that and hand it in, because in this lesson we're going to be continuing, we're going to be building on that knowledge of the nucleus and of nuclear physics in general. Now on the screen I've just put a basic idea, a basic model of what an atom looks like. In the centre of our atom we know that we have a nucleus, and that nucleus is made up of two different particles. It's made up of protons, neutrons, and that orbiting around the nucleus we have electrons. There is a collective term for protons and neutrons that we use, and it is the word nucleon. And as I said, nucleon is just a collective term for protons and neutrons. Now, interestingly, on the screen we do have a model of the atom. It isn't strictly the same as the model that Rutherford came up with in 1911. This is probably more along the lines of Chadwick's model of the atom, which he came up with in 1932. The model of the atom has gone through several revisions and several updates since Rutherford came up with his model back in 1911. Firstly, Niels Bohr came up with the idea of electron orbits in 1913, a couple of years after Rutherford's model. Schrödinger then in 1926 came up with the quantum model and looking at how electrons are quantum particles. And if you did the extension task for Electric Fields 3, you'll have heard me talk about the idea of electrons behaving as waves as they're orbiting. And then Chadwick's model, which is very similar to what's on the screen, was in 1932, a little bit later on. Moving away from the history lesson then, the first thing we're going to look at today is nuclear notation, which is a way of writing down what's inside a particular nucleus, and obviously is an effective communication tool when we're talking about nuclear physics. Now, the general way that we write down a nuclear notation is like this. Now, these are obviously just generic letters at the moment, but we'll explain exactly what they mean. The X at the centre will represent the element and just gives you the name of the element itself. So if we just take an example of uranium, uranium will be a capital U. The second number that we care about is the Z, which gives us or shows us the proton number. The proton number is exactly what it says. It is the number of protons that are in that particular nucleus. For uranium then, there are 92 protons in a uranium nucleus. The next one is A, and A is the nucleon number. The nucleon number, of course, from the last slide is the number of nucleons, so the collective number of protons and neutrons that are in that particular nucleus. So for uranium, I will just pick 2, 3, 8 for now. Some of the other numbers that you may see associated with nuclear notation that we don't necessarily use in nuclear physics, you may see a charge placed at the top right. That tends to be used more in chemistry when they're looking at ions and such like. And sometimes you'll see N placed at the bottom right, which is the neutron number. We don't need to put the neutron number there because we can calculate the neutron number from the proton number and the nucleon number. Remember that because nucleons are a collective term for protons and neutrons, we can apply the equation A is equal to Z plus N. And you can rearrange that easily to say that N is equal to A minus Z in order to calculate how many neutrons there are in a particular nucleus. So in the uranium nucleus that we've been using as an example, there are 238 nucleons, there are 92 protons, and that therefore means that 238 minus 92 is 146, and there would therefore be 146 neutrons in that particular nucleus of uranium. Now, bringing back the example that we had on the last slide, 2, 3, 8, 92 and U for uranium, the way that that would be communicated verbally would be to say uranium 238. And sometimes you'll also see it written as uranium-238. Now, what happens if we start to change these numbers? Firstly, let's think about what happens if we change the proton number. Let's just pick another number, 6. Now, if we have 6 protons, then that makes carbon. Changing the proton number fundamentally changes the element. We can pick another example and take oxygen. And in oxygen there are 8 protons. So the number of protons determines what the element itself is. As you change the number of protons, you change the element itself. As far as the nucleon number goes, though, we can change that without actually changing the element itself. Let's take another example of uranium, which we know has got to have 92 protons in. But we can very easily have another nucleus of uranium which only contains 235 nucleons. Obviously we know that from a neutron point of view there are 146 neutrons in uranium-238, whereas there are only 143 neutrons in uranium-235. What we've just described therefore are 2 different isotopes of uranium, and you can see on the screen we've got the definition for what isotopes are. Isotopes are atoms of an element with the same number of protons but a different number of nucleons. Taking our 2 isotopes of uranium, uranium-238 and uranium-235, they are both still uranium because they both contain 92 protons. But as we said, they contain a different number of neutrons and therefore a different number of nucleons, and they then become different isotopes of uranium. To look at how that affects carbon, we can have carbon-12 and we can also have carbon-14, which are 2 common isotopes of carbon. For oxygen, the most common isotope that we get is oxygen-16. You can also get a little bit of oxygen-18, and there is even some oxygen-17 which occurs naturally as well. After Rutherford had discovered the nucleus, he went on to build upon Marie Curie's work in looking at nuclear radiation. Now, nuclear radiation comes in the form of different particles that are emitted from the nucleus. The reason why nuclear radiation occurs is one of the topics that we will move on to look at in more detail as we move through this topic and delve deeper into exactly what nuclear radiation is and how it works. Now, Rutherford discovered that there were 3 types and 3 different types of radiation, and they were named after the first 3 letters of the Greek alphabet: alpha, beta and gamma. Now, if we go on just to complete this table and look at exactly how these 3 work. An alpha particle is made up of 2 protons and 2 neutrons. A beta particle, well, there are actually 2 different types of beta particle. We can have an electron or we can have a positron. If it's an electron, then we call it beta minus, and if it's a positron, we call it beta plus. The one key thing to know though about beta particles, whether they be beta minus or beta plus, is that they are very high energy and therefore they move very fast. A gamma particle is an electromagnetic packet of radiation. And again, it comes on the high energy end of the electromagnetic spectrum. In air, they all have differing ranges. An alpha particle will go a few centimetres before it is absorbed and loses energy due to collisions with the particles of air. A beta particle will go of the order of metres, so it will go a few metres before it's absorbed, whereas a gamma particle has pretty much got an infinite range in air. In order to absorb these particles, for an alpha particle, a piece of paper, a standard piece of paper, will absorb the vast majority of alpha particles. For beta particles, you're looking at a few centimetres of aluminium will do the job there. For gamma, you will need a pretty substantial chunk of lead in order to stop gamma. Lead, of course, being one of the most dense metals that we can extract. Or you're going to need several meters of concrete in order to stop the gamma particles. Now, the final column, the ionisation column, is going to show us how many ions these three particles cause in air. In other substances, the ionisation level will be different, so this is just the ionisation in air. Now, alpha particles, for every millimetre of air that they travel through, will create approximately 10 to the 4 ions, so about 10,000 ions. For beta particles, they will create around about 100 ions per millimetre, and for gamma's not very ionising at all, so you won't get that many, and it's one of these that per millimetre is going to be very few. Sometimes in a millimetre it might not even create any ions whatsoever, so the number is very small. What we can see then is that the alpha particles are the largest, so size increases as we go up the table. The ionisation level, the ionisation potential, increases as we go up the table, but the range increases as we move down the table. In other words, the alpha particle creates a lot of ions, but in a very small space, a very small range, whereas a gamma particle won't create many ions, but will travel through quite a lot as it goes through and ionises. Next then, we need to look at what effect these three types of radiation have on a nucleus when they're emitted. Firstly, and logically, first we will look at alpha decay. Now, if we start with a generic nucleus, a ZX, okay, and this is just generic at first. When that nucleus decays by alpha decay, it will emit an alpha particle. Now, an alpha particle contains 2 protons and 2 neutrons. Therefore, we can put on our alpha particle the numbers 2 in place of the proton number because it contains 2 protons, and 4 in place of the nucleon number because it contains 4 nucleons, 2 protons and 2 neutrons. What we're left with then is a different nucleus. Now, the way to view these decay formulae is just the same as mathematical equations. We've got 2 different lines that we need to make sure mathematically look correct. We need to make sure that the nucleon line on the top looks correct, and we need to make sure that the proton line on the bottom also looks correct. The arrow in our equation can be treated exactly the same as an equal sign. From chemistry, we know that whatever we have on the left-hand side of an arrow in a chemical formula must be exactly the same as what we have on the right hand side. It will just be organised in a different way. Therefore, on the top line, we're starting to build an equation. A is equal to something plus 4. Now, in order to make this equation mathematically look correct, we've got to insert into there A minus 4. Our nucleus has therefore lost 4 nucleons, and the new nucleus will have A minus 4 nucleons remaining. By exactly the same logic, on the bottom line, we can put Z minus 2, because we can see that Z is equal to Z minus 2 plus 2. Because the proton number has changed, the element itself has also changed. So I'm going to denote that using the letter Y to show that it's no longer element X. We now have a new element. The technical term for these nuclei then are the parent nuclei, is the one that we start with before it's decayed, and the daughter nucleus is the one that it decays into. Those are just technical terms to describe parent and daughter. Those are just the nuclei and some technical terms that we can use. Now, to give you an example of alpha decay, if we take uranium-235, which we've already looked at, if that decays by an alpha mode, then what we're left with on the top line is 231. We've removed 4 nucleons at that point. We've also got to remove 2 protons at the bottom to get to 90 on the bottom. And 90 obviously isn't uranium anymore, it is thorium with the symbol TH. Moving on to beta decay then, we obviously need to make sure that we look at the 2 different types. So we'll look at beta minus decay first. In beta minus decay, we have got an electron that has been emitted from the nucleus. We will once again start with our generic nucleus, AZX. And that will decay into a beta minus particle. Now, inside the nucleus, we need to think about what exactly changes. Logically, and hopefully from last year we know, that a neutron is decaying into a proton and an electron, and in order to make sure that we keep everything conserved, an anti-electron neutrino. Now, because a neutron is decaying into a proton, our proton number will increase to Z plus 1. Because our proton number has changed, we're once again changing the element, so we're going to put a Y there in order to show that the element itself has changed. However, for the top line, for the nucleon line, a neutron is being lost but a proton is being gained, so there is no net change in the nucleon number itself, so we're just left with A. Because I'm a particle physicist, I'm just going to leave that anti-electron neutrino in there just to make sure that all of our numbers are conserved. For beta plus decay, we have a positron being emitted. Now, for the positron emission, neutron plus positron plus electron neutrino. So proton decays into neutron plus electron, plus positron plus an electron neutrino. Once again, if we take our generic nucleus AZX, we are losing a proton, so our proton number becomes Z minus 1 and we have another element change again. But just like we said with beta minus decay, we're keeping the same number of nucleons and therefore our nucleon number remains the same. We have emitted a beta plus and, once again for completeness, an electron neutrino. To give you an example of I'll just give you one example for beta plus decay. Let's take oxygen 18. And when that decays, well, the proton number will drop to 7, but the nucleon number we know will remain as 18. For 7 protons, it's obviously not oxygen anymore, it will now be nitrogen, and we know that we also have a positron and an electron neutrino emitted. Finally, for decay formulae, then we need to look at gamma decay. Now, for gamma decay, because we're only emitting a photon, because we're only emitting a packet of electromagnetic radiation, there is no fundamental change to the protons or the neutrons in the nucleus, and therefore our nucleus stays exactly the same. The only difference, and sometimes you will see an asterisk placed up here, is to say that we are moving from an excited state, so where the nucleus has more energy than the ground state, and we are moving down to a lower energy level in the nucleus. So now on to an example. A uranium-238 nucleus undergoes alpha emission, immediately followed by the emission of 2 beta minus particles. What is the final product of this decay chain? As usual, please pause the video, have a go yourself, and then come back once you've got an answer. So firstly then, if we take uranium-238, 23892U, and we'll do the alpha emission first. So alpha emission, put the numbers on, 4 and 2, will leave us with 2, 3, 4 and 90. And we saw earlier that 90 protons is thorium. Now we need to do 2 lots of beta minus decay. So we start now with the thorium 234. And we will do a beta minus decay first. The nucleon number stays the same, and in beta minus decay the proton number increases by 1 to 91. Now that element is Pa, protactinium. The good news is that you're not expected to know what the element names for any given proton number are. They will either be given to you in an exam, or you'll simply be given them, no need to remember them whatsoever. We'll then do the second decay by beta minus, so 234 91 protactinium. Once again decays by beta minus with an anti-electron neutrino. The nucleon number once again stays exactly the same, but our proton number goes up by 1 again when we're back to 92, which we know is uranium. So the final answer, the final product of this decay chain, is uranium 234. Now in nature that's actually quite a common decay chain. Uranium 238 decaying by an alpha and a couple of beta minuses, it still ends up as uranium, just a different isotope of uranium. So to summarise then, the 3 key things that we've looked at today are nuclear notation, and for nuclear notation we use the format AZX, where A is the nucleon number, the number of protons and neutrons that a particular nucleus contains, and Z is the proton number, the number of protons that are in that particular nucleus. We also looked at isotopes, and again you've got the definition for isotopes on the screen that we looked at earlier. And then finally we looked at the decay equations for alpha, beta minus, beta plus and gamma decay. So that's all for this lesson. Hope you've enjoyed that. Obviously, as usual, any questions please let us know, and I'll see you next lesson.